the audio quality
Hello,
is good?
everybody. Good evening and good morning, those who are watching from USA. So, welcome to our international physics webinar. And today it's our 268th international physics webinar, and I'm happy to share with you that today we have with us Dr. Anil Chandra Seth, sir, Associate Professor, Department of Physics and Astronomy, University of Utah, USA, and he has already connected with us. So, sir, good morning, and thanks
Good
for
morning.
joining with us. So it's our pleasure, sir, that you have given us time with a very exciting topics. So I
All right.
think our student and viewers will enjoy it. So dear student and viewers, I think you have already come to know the title, and title is very exciting: Black holes in a low mass galaxy. You can also join with us using the link. I'll send the link in the comment section, and you can also ask question by commenting. So please enjoy this exciting lecture. Sir, it's your time. You can start your session.
Okay, great. So I will go ahead and start here. This hopefully now is full screen for you.
Yes, yes.
Okay, great. And like Kumar said, if you have questions in and you can put them in the chat, and he'll interrupt me, and if they're kind of necessary at the moment, then and to clarify things, please just go ahead and ask those questions right away. And otherwise, we'll chat at the end.
Yeah.
Okay, so I'm going to tell you today about research that I'm doing on trying to find black holes in small galaxies, and I'll kind of explain what counts as a small galaxy as we go along here. So black holes are, pretty simple, a pretty simple concept actually. If you try to launch a rocket from the surface of the Earth, it takes you need to launch it above around 10 kilometers per second, which is the escape velocity of the Earth. And as if we shrink the Earth, the gravity gets stronger. We're getting closer to all that mass, right? So then we need a higher escape velocity in order to escape that stronger gravitational field from the surface. And so if you keep shrinking all the more and more and more, the escape velocity keeps getting higher. And once it is faster than the speed of light, at that point we have a black hole. So that's the very simple explanation of what a black hole is. As you for the sun, you'd have to shrink this down to be about 3 kilometers in radius before it would become a black hole. And because of the fact that light can't escape, the only things we can measure about black holes are their mass and their spin. Just give me 1 second. I think I have one problem here. It's going to create. Okay, perfect. Okay, so we know of two kinds of black holes. The first are what I think of as kind of ordinary black holes. These are called stellar mass black holes, and they're born in supernovae. We know that when a supernova blows up, sometimes the core of the star is left behind as a black hole in the process of that explosion. And millions of these likely exist in our galaxy. On the other hand, the kinds of black holes that I'm going to be talking about are often referred to as supermassive black holes. And these are black holes that we find at the centers of galaxies. And this is the famous galaxy M87 in the Virgo cluster. It's the very largest massive elliptical galaxy in the nearby universe. And we can see at the center already there's something funny going on. And as we zoom in, we can see there's these jet-like structures. These are generated, we think, by material falling onto this supermassive black hole. And then recently, and I think this was in the intro slide, right? There's this very famous image that's been constructed from the Event Horizon Telescope. And that is probing actually the shadow of the black hole, really down to the kind of scale of the innermost circular orbits of the black hole, and that image really proves that there is actually a 6 billion solar mass black hole in this galaxy. So 6 billion times the mass of the sun. So very, very, very much more massive than a stellar mass black hole. And these supermassive black holes can be very, very bright. So they were first discovered as quasars, which were point-like sources back, and people in the 50s realized that these were at some of the most distant objects that they could discover through the patterns, through the redshift of the objects, the patterns of their emission lines. And these, in some extreme cases, these can be 100 times brighter than the entire Milky Way galaxy, the black holes at the centers of galaxies, when a lot of material falls onto them. On the other hand, the black hole at the center of our Milky Way galaxy is really almost invisible. So here's the right-hand side is a X-ray image of the center of our galaxy, and you can see that there's just a very a faint source that's one of many sources of similar brightness at the center of our galaxy, and that is because the black hole has very, very little material falling onto it, and we would never be able to detect it from this X-ray signature beyond if it weren't in our own galaxy. So, for stellar mass black holes, I told you exactly how they form right away. They form from supernovae. For supermassive black holes, we do not know the answer to that. We do not know how they form. There are a wide range of models for how they form. One of the models is that that the very first stars in the early universe because they have no metals in them yet, so they're just hydrogen and helium, they end up likely having larger masses than the stars that we see today, and that could create extra big black holes when they explode. Those first stars could create seeds of up to about 300 solar masses or 300 suns. On the other hand, there's a kind of a model where in the early universe, if you can keep the gas from fragmenting, it can directly collapse down into a black hole that's something like 10,000 to 100,000 times the mass of the sun. So these are a couple ideas. There's additional ideas, and there could be a mixture of these things that are generating the supermassive black holes that we see in today's universe. But the curious thing that we have here is that we, from the black holes that we know about, we have a lot of black holes that are somewhere between, typically like 10 times the mass of the sun, 10 solar masses. So you'll be seeing the solar mass symbol here throughout the talk now. And so I'm just introducing you to that. So, we have black holes that are something like typically 10 solar masses that are these stellar mass black holes. And then we have black holes that are typically above 1 million times the mass of the sun. The one in the Milky Way is actually about 4 million times the mass of the sun. And there's this huge gap in the middle here. And this gap is often referred to as intermediate mass black holes. And that's kind of the kind of range of black holes that I'm going to be talking about, things that are between 100 and 1 million solar masses. So, the question is, do we expect intermediate mass black holes? And in these different mechanisms for making the supermassive black holes, we get different expectations. So for this first stars scenario, we would expect that if the supermassive black holes all started smaller and they grew over time, that some of those objects just wouldn't have grown as much. And so there should be a lot of intermediate mass black holes. However, if that scenario doesn't really happen, for instance, the first stars aren't as massive as we think they might be, they don't produce as many black holes as massive of black holes as we think they do. Those things are very uncertain. Instead, if there's this direct collapse kind of scenario, we expect there to be fewer intermediate mass black holes. That most of the black holes, if they already start at 100,000 solar masses, of course, are going to be more massive than that, and there should be very few objects in that, or maybe even no objects in that intermediate range. So you probably have heard of the LIGO measurements of black holes. So this is a very exciting development over the last 5 years, which is that we've detected the stellar mass black holes colliding with each other, actually merging together. And in that process of merging, they create these distortions in space-time that we can measure as the y-axis here is actually the strain in the detector, but you can think of it as the effectively a change in the distance on Earth. And so we can detect these using these black holes using interferometers. And we've discovered a lot of these black holes now. So all of these blue objects on this plot of where the x-axis doesn't mean anything, but the y-axis is the mass of the black hole. And you see that there's a lot of objects where there's two gray lines connecting to a top black hole. That's the two merging black holes then merging together to form one big black hole. And what you can see here is that the biggest of these now is into this kind of intermediate mass black hole regime. And there's a lot of really excitement about this. I went to a conference last month that was talking about, how can you actually generate black holes this big? We actually don't expect to have progenitor black holes kind of even above about 60 solar masses. And so the fact that these black holes are merging might mean that this is the kind of second merger of these black holes. And that's hard to pull off in the kind of typical scenarios where we think black holes live and what happens to them after they merge. So, this is an exciting thing that's happening right now in black hole astrophysics. It's not what I do research on, but it is pushing us into the intermediate mass black hole regime from the low mass end. So the techniques that I'm interested in using are to measure black holes by the influence of this that they have on the stars around them. So here's the center of our Milky Way. And what's shown is a movie based on observations of positions of stars at the center of the galaxy over time. And you can see that the time is shown here on the upper right. And it's about a 20-year time period. So I'll run that again, a little bit more than 20 years. And what you can see is that some stars that are pretty close to this central star here have actually orbited all the way around the black hole. And that gives us a very strong constraints on the orbits of those stars and therefore the mass enclosed in those orbits. And so we know that there is a point source at the location of that star, and that its mass is about 4 million times the mass of the sun. And so this is called a dynamical detection because we're using the motions of the stars in order to constrain the black hole mass. Beyond the Milky Way, we don't have any way of looking at individual stars. Instead, we can only look at the collective motions of groups of stars. But even though the motions that I'm showing in this movie here we're not seeing the individual motions, on average, these stars are moving at about 1,000 kilometers per second in this image. And that is much faster than anywhere else in our galaxy. So if we were able to see this collection of stars, the light from the stars, we would see that their light showed extreme Doppler shifts at the center, even if we couldn't see the individual stars. And so that is the way that we measure black holes beyond the Milky Way. And in particular, what we do is we use very high resolution imaging, typically from the Hubble Space Telescope, to tell us the stellar mass profile, essentially to see where stars are distributed. And we use that to create a dynamical model and predict how fast the stars should be moving. Then we go to the high resolution measurements of the motions of stars, and I'll talk about how we get that in a minute. And we use Doppler shift measurements to actually measure what we call the velocity dispersion, which is the kind of spread in velocities along our line of sight. And that allows us to get to see how fast stars are moving at different radii in this galaxy and compare it to the prediction that we have from the stellar model. And we can then add in a black hole and see if into our model and see if that predicts the motions of the stars better. All right. So, I told you about the black hole in the Milky Way. It's about 4 million times the mass of the sun. Most galaxies are actually much less massive than the Milky Way. So what this plot is showing you is the number density of galaxies per unit volume in the universe. And the Milky Way is shown here. And you can see that at lower masses, there are many more galaxies per unit volume. So for every Milky Way-like galaxy in the universe, there's many smaller galaxies. And so, the typical galaxy in the Milky Way, in the universe, is actually much less massive than the Milky Way. But we don't know very much about their black holes that live at the centers of these galaxies. So, here's an image of the Virgo cluster. I've shown M87 is shown there. And almost all of the very small fuzzy blobs in this image are galaxies, many of which are, smaller than the Milky Way. And the question that my research is really focused on is, do these little galaxies have black holes in them or not? At their centers or not? And this is an interesting question because it can help us constrain these different scenarios. So this is showing the fraction of galaxies that have central black holes in the case of these two different models that I talked about earlier. This direct collapse model on the left-hand side, where very few massive black holes are produced, or the first stars model, where we expect these kind of seed black holes, the initial black holes that help form these central massive black holes. If they're present, we expect them to be abundant. And so therefore you have at low masses, which is the left-hand side of these panels, there are fewer black holes in this direct collapse scenario than in the first star scenario. And so, measuring whether these low mass galaxies have black holes or not is of interest for understanding the formation of supermassive black holes. The other thing is that, from what's shown here is a plot of the measurement of all of the dynamical measurements that we have of black hole masses in nearby galaxies. And the y-axis is the black hole mass. The x-axis is tracing essentially the galaxy mass. So here you can see that most of the galaxies we found black holes in are actually more massive than the Milky Way, which is down here. And there's this really tight correlation, and this correlation is related to the fact that we think that it's created by the fact that black holes actually regulate how many stars can form in a galaxy. So black holes are much, much smaller than galaxies. In our Milky Way, once you go just a few light years away from the central black hole, you no longer are dominated by the gravity of the black hole. Instead, you're dominated by the gravity of all of the stars in the nuclear cluster of the Milky Way, and then into the bulge of the Milky Way. And from our distance, at 8 kiloparsecs, the only way we can tell that there's a black hole there is by observing stars right very close to it, right? So we don't really have any information about the black hole shouldn't be influencing what's going on at our position in the galaxy, but yet we see this correlation between the black hole mass and the galaxy's properties. And we think that that's because black holes are so efficient at turning mass into energy that when there's a big episode of star formation, the black hole also has material falling onto it. It lights up as a quasar and feeds back on the rest of the galaxy. And so that is, one of the things that we are very interested in finding out about low mass black holes is, does this stop to work at these low mass galaxies? In that case, we would expect to see a really large scatter here of some low mass galaxies have big black holes, others have little black holes. So this is a kind of a typical low mass spiral galaxy. And we're going to show, I'm showing you a Sloan digital sky survey image, which is kind of a typical ground-based image. And then we're going to shift to a Hubble Space Telescope image. And what you can see as we zoom in here is that right at the center of this galaxy, there's actually a very bright kind of American football shaped object here. Or an M&M shaped object maybe. And this object is actually a dense star cluster. the central density of this star cluster is about 1 million times the density of the rest of the galaxy at that location. And we're really lucky these star clusters exist because it allows us to probe the black holes at the centers of galaxies more easily than we would otherwise. And these nuclear star clusters are something that I do a lot of work on. I was part of a review article on these dense star clusters that we find at the centers of galaxies that are very unique. What we found is that most galaxies, so the Milky Way is on the kind of right side of this diagram, and most galaxies at lower masses do have these nuclear star clusters until we get down to very, very low masses. So the typical galaxies that I'm going to be talking about in this talk are kind of 10 to the 8 to 10 to the 10 solar masses, and in this mass range, the nuclear star clusters are typically more than 1 million times the mass of the sun, and their mass actually correlates with the galaxy they live in, just kind of loosely, but still a pretty clear correlation. So these nuclear star clusters are really valuable because they allow us to have probes of the gravity right near the center of the galaxy, nice bright probes that we can observe with our telescopes. And so kind of now getting to the observations that we can make, the key here is to get the observations of the motions of stars very close to the center of the galaxy. So we need to have very high resolution observations. We need to be able to distinguish from the stars right at the center from those just a little further away. And, in that context, if you ever, look up at the stars and you are seeing them twinkling, that twinkling is actually horrible for us because that twinkling ends up blurring out the images of the stars. So what's shown here is actually the Gemini telescope on Mauna Kea, which is the telescope I've used for a lot of the work I'm going to be describing here. And that orange line that's coming out of the top is not photoshopped in. It's actually a laser that's being shot into the ionosphere. It's ionizing sodium atoms in that ionosphere, and that ends up creating an artificial star right next to our target. And we can use that artificial star in order to try correcting for the twinkling of the stars, essentially the distortion caused by the Earth's atmosphere. And using a very flexible and rapid mirror, we can essentially undistort the image. This is called adaptive optics. And this allows us to get close to the diffraction limit of the telescope, which otherwise we can only do from space. So the reason why the Hubble Space Telescope is so great is we don't need this technique because we're above the atmosphere, and we just get as high resolution images as the 2.4 meter mirror of the Hubble Space Telescope can give us. This is an 8 meter telescope. It should be able to give us even sharper images, except for the Earth's atmosphere. And that is, yeah. Okay, so just to remind you, the piece I'm describing to you is how we get these observations on the right. And so we use that Gemini telescope paired with what's called an integral field spectrograph, which gives us the spectrum in every pixel near the center of the galaxy. And that allows us to create this measurement of the motions of stars that we need. So one problem in low mass galaxies in general is that the stellar mass profile, this kind of left-hand part of this, is actually not that easy to determine. And the reason why is that the star light helps us trace the star mass in an object, but that can vary from position to position in the galaxy. So in some areas you might have bright young stars. Those even though we have lots of light, we might not have that much mass. Other places might be dominated by old stars. There, a little bit of light can mean a lot of mass. And the other thing that can happen is we can have dust, which blocks our view of the light. And that also makes the light redder. And so in general, we can look at the color of the light and it gives us some indication of how much mass is at that location. Redder pixels in this image are likely to be more, which are these kind of the top, these yellowish colors are actually redder pixels in this image, and these purplish bluish colors are the bluer pixels. And we can change the mass to light. We can understand how the mass is distributed by very carefully looking at the colors, and even better, getting spectra. And so this white line is showing a Hubble Space Telescope spectrum that we've gotten of this galaxy, where we can actually model exactly the stars that are there in order to figure out how much mass is at each point in the image. And so this is something that my student Yu Nguyen has done a lot of work on. Former student, he's now a postdoc, has done a lot of work on. Once we have that, we can determine the black hole mass. We can use this dynamical modeling to fit a black hole mass, as well as as essentially measure how heavy the stars are. And what you're seeing on this diagram here is the measurement of the velocities as a function of radius in this one galaxy, and then the red line is our best fit model to that data, and the lower black line is the best fit model if there was no black hole. And so you can see that at the center, the stars are moving about quite a bit faster than we would expect if there was no black hole. And this is the kind of evidence for the black hole that we have. And this axis on the right-hand side includes both the motion from rotation and the motion of along the line of sight. So we can take our models and vary several different parameters. The two that are most important are how heavy the stars are, which can impact how heavy the black hole is. So because essentially we can, if the black hole is a little lighter, that might mean that we can fit a model that works pretty well where the stars are a little heavier, and vice versa. And so what you can see here is the measurement of the black hole in that same object. And you can see that its black hole mass is something just under 1 million solar masses. And the stars are weighing pretty much what our model thought they should weigh, very close to 1 there. So that's the kind of technical details of this process. What we found is by looking at these galaxies here. So this is, you can see there are 6 galaxies pictured here where we've measured black holes. And we found really strong evidence for black holes in 5 of the 6 of these galaxies. And these tells us that black holes are common in galaxies that are similar mass. These are all 10 to the 9 to 10 to the 10 solar mass galaxies. And this tells us that at least half of galaxies in this mass range are likely to have black holes in the universe. And these are also the first dynamical detections of black holes below 1 million solar masses. So several of these have black holes that are below 1 million solar masses. So one thing that in the kind of process of doing this work that has happened was we found a kind of a surprising result. And that result is related to this movie that I'm going to show to introduce it, which is when we have a really big galaxy, other big galaxies are typically formed from the mergers of smaller galaxies. And as a small galaxy falls into a big galaxy, the tidal forces, so the differential gravitational force from the big galaxy is actually large enough to rip stars off of the smaller galaxy. And it can do that very efficiently if it passes close enough to the center of the galaxy and actually strip away all the stars except for that nuclear star cluster that I was telling you about earlier, that I showed in that previous movie. And so we think that there should be these stripped nuclear star clusters. So we strip because they've been stripped away of all of their outer layers, and they should be floating around massive galaxies. The problem is that these things look a little bit like globular clusters. And so we don't know, just looking at an object, whether it is a stripped nucleus or not. So one thing that we found back in 2014 was we took observations like the ones I talked to you about, adaptive optics observations, to measure the motions of the stars in that object that I just showed you in the previous movie. It's called M60 UCD1. The UCD stands for ultra compact dwarf. It was It's a very massive star cluster that people had started calling ultra compact dwarfs. What you can see here is that on the right-hand panel, it shows that the motions of the stars right at the center of this object are much, much faster than in the rest of the object. And this is turned out to be the signature of a 21 million solar mass black hole. So, for comparison, the Milky Way galaxy has a black hole that is 4 million times the mass of the sun. That's about 0.01% of the total galaxy mass. In this object, the black hole mass is 21 million solar masses, and that is 15% of the total mass of that ultra compact dwarf. So there's about 100 million solar masses of stars there. So this is a case where this object is pretty clearly a stripped galaxy nucleus, because we don't expect to be able to form this big a black hole in any other way than at the center of a galaxy. Okay. And so we've been doing follow-up work on this, and what we found is that basically we found black holes in almost every object that we've looked at them as above a certain mass. So this shows the mass of the object, the essentially of the star cluster, and you can see 10 to the 7 is here, 10 to the 6 is here, 10 to the 8 is here, and above 10 to the 7, we found that every object we've looked at, we've found evidence for a big black hole in them. And so we think that essentially all of the objects above this mass that are floating around galaxies, all the compact star clusters that are above 10 million solar masses, all of them are actually stripped galaxy nuclei and have these big black holes. And these lines here are the percentage of mass of the object. What you can see is at the bottom end, it's harder to find. These black holes are littler, so they influence a smaller area in the cluster and have a smaller impact. And that means that the black holes are more difficult to find. But one object, so these two blue lines are actually upper limits that my former postdoc, Karina Vogel, published a little while ago. And this red star is a measurement that I'm going to talk about next. So this is a detection of an intermediate mass black hole in Andromeda's most massive cluster. So this is you can see here, this Andromeda famous picture was on the background of computer screens for a while. There's a very dot here that turns out to be a very massive star cluster. It's about 6 million times the mass of the sun. It's the most massive star cluster in Andromeda. And that star cluster, here are the motions of the stars there. And through careful analysis of the motions and modeling of the stellar mass profile of the cluster, we have determined that there's a 100,000 solar mass black hole at the center of that cluster. And that's additional evidence of being a tidally stripped cluster. And there is also additional evidence of being a tidally stripped cluster. It's still very early here. So, okay. So what we've been, working on is kind of, from LIGO has kind of shown us that there are black holes now above 100 solar masses. And the work that I've been doing has been kind of pushing this limit of dynamical measurements of black holes down well below 1 million solar masses. And it turns out, that what's next? Are we going to be able to find more of these objects? And the challenge is that the same techniques that we're using to find these black holes at the centers of galaxies will stop working at some point. And part of the reason is that it becomes, as we get smaller and smaller signatures of black holes, it becomes more and more ambiguous whether what we're seeing is a single black hole or a collection of stellar mass black holes, which we also expect to collect at the center's lower mass star clusters. And so I've been kind of thinking about other ways that we can probe this mass regime of black holes and really understand the population of black holes at the centers of galaxies down to lower masses. I wanted to, sorry, this is from, I copied these slides and I realized I hadn't updated. The James Webb Space Telescope, in case you didn't hear, has launched in December. And the Vera Rubin Observatory, which is going to have first light next year. And so I'm going to talk about two different opportunities with these two different telescopes that I'm hoping to work on, and why they might help us understand this problem better. So opportunity one, JWST. What's shown here is the sensitivity to emission lines as a function of wavelength. And this is starting at the left-hand side is the optical part of the spectrum. And then the rest of it is the infrared part of the spectrum. So at infrared wavelengths, the telescope I was just talking about, Gemini here, and other large telescopes have a sensitivity, that is here, while JWST will have a sensitivity that's almost 2 orders of magnitude lower at many wavelengths. And at wavelengths kind of around 5 microns here, you can see that there's essentially no other previous facility that's had anywhere close to the sensitivity that we will be getting with JWST. So it's, busy unfolding its mirrors and stuff now, but soon we will be getting hopefully extremely sensitive infrared measurements with JWST. And so you might wonder, is this good for detecting black holes? And the answer is yes. In particular, most black holes in the universe are like the black hole at the center of our Milky Way. They aren't emitting a lot of light because not a lot of material is falling on them. We call these things low luminosity AGN. But it turns out that low luminosity AGN are very bright in the infrared. So, when material falls onto a black hole, it emits light across the electromagnetic spectrum. So often people use X-rays to probe the black hole, to probe AGN in galaxies. Their AGN stands for active galactic nuclei. So it's just when black holes light up. And you can see here at the in the high luminosity end, there's a lot of these black holes emit both a lot of X-ray luminosity, and they also emit a lot of luminosity in the infrared part of the spectrum. And my student Antoine Dumont, who's just finishing up this year, his PhD, showed that actually, as we get to these low luminosity objects, we do see evidence for very bright emission in the infrared. And in fact, the emission that often exceeds the X-ray luminosity. And so it turns out that James Webb may be the most sensitive way of detecting these low luminosity AGN that we have. And just to kind of, I told you that the typical galaxy is not accreting very much material, meaning that not much material is falling onto it. This is a distribution of galaxies in the local universe, and what's on the x-axis is how bright those black holes are relative to the maximum brightness they could have, which is called the Eddington limit. And you can see that there's the typical quasars and Seyfert galaxies, what we call typical AGN. Those things are all above about 1% of their maximum, are radiating at nearly 1% or more of their maximum luminosity. But the typical galaxy in the universe is more like 100,000th of that maximum luminosity. And so these, if we want to probe the typical galaxy through looking at their AGN, we need to be able to detect galaxies that are low luminosity AGN. And to do that, I have a JWST program that will be starting to be observed this summer to observe these 7 galaxies that are shown here in green circles. These are nearby famous galaxies. One of them is M87. And the idea is to get spectra of 7 well-known but weakly accreting black holes at JWST wavelengths. And so the basic idea is we don't know what these AGN look like at these wavelengths. And what we want is templates for how they're going to look in other places, so that we're able to look at some object and say, yes, that's definitely a black hole. And in addition, so that's the kind of my main interest, is identifying these unique signatures of black holes at the centers of galaxies. In addition, this data will be extremely helpful for understanding the structure of these low luminosity AGN, which we don't understand very well, through both the continuum emission, essentially just the light that's coming out from them at infrared wavelengths, and also the emission lines that result from the light at other wavelengths. For instance, the UV light ionizes atoms, and those atoms then emit emission lines in the infrared part of the spectrum that we should be able to detect. And those might actually also be useful as unique signatures of these black holes. So that's one opportunity that I'm really excited about. I'm hoping that we'll then in future cycles be getting data on dwarf galaxies where we don't know that there's a black hole, and we can verify that using JWST. Opportunity 2 is this Vera Rubin Observatory. It's named after Vera Rubin, who is the person who demonstrated that dark matter is present in typical galaxies through the rotation curves of their galaxies. This is going to be an imaging telescope. It's an 8.4 meter telescope plus a 3.2 gigapixel camera. It'll be the largest camera in astronomy. And that'll enable us to get an image of the full sky every 3 nights. And the kind of incredible thing is that we'll be getting 20 terabytes of data every night. And this is going to be revolutionary for identifying transient events that happen just for a short period of time, variability in the sky. So when there's a specific kind of transient event that I'm particularly excited about, and it's called a tidal disruption event. And this is when all of a sudden, it's like you go to this black hole is just sitting around and it gets a nice cold drink and it slurps it all up at once. And what really happens is that a star comes so close to this black hole that the tidal forces of the black hole actually rip the star apart. And some of the material from that star will then fall onto the black hole over the period of the next year or so. And that will create a flare that looks like, in luminosity, it's a lot like a supernova, but has some distinctive features. And we think that actually one of the best intermediate mass black hole candidates that we have is actually probably a tidal disruption event. It's this object HLX1. It's an X-ray source in this nearby Edge-on galaxy, and you can see that this is the source right here, and it's variable in a kind of periodic way that suggests it's actually a tidal disruption event. And we think that in general, tidal disruption events will be very useful for probing these low mass black holes. So, the picture at the left kind of shows what we think happens. The star comes close to the black hole, it gets tidally distorted, and it passes within the tidal radius of the black hole. And that tidal radius, once it passes within there, it gets ripped apart, and some of the material ends up falling. Essentially, all of the material that's inside this dashed line ends up falling back onto the black hole, and the other material escapes. And we've been detecting these objects in the last decade. So here is some examples of objects that have been found at the centers of galaxies that agree well with the predictions of this tidal disruption and being these tidal disruption events. And what's shown is their luminosity on the y-axis, and you can see they range really widely in how bright they are. And we detected about 50 in the last decade. But with Vera Rubin, we expect to detect 10 every night. So that is pretty incredible. So this is a real opportunity for studying black hole demographics. And basically Rubin will be able to find TDs and tell us about their hosts. So and also we can find out about the black hole masses from the events themselves. But the problem is that these tidal disruption events only happen in galaxies once every 100,000 years or so. And so the rate depends very sensitively on how dense the stars are right around the black hole. Basically, the higher density, the more often you'll get in a TD event. And this is really those nuclear star clusters I was talking about. Again, if we look at the density profiles of nuclear star clusters, and this is work from my former student, Renuka Pichetti, who also published that IMBH result in Andromeda. So this is work that's showing the very nearest nuclear star clusters, probing the 3D densities on the scales that we need to really predict the rates of tidal disruption events. And what you can see here is these are colored by the galaxy mass, and it looks like there's this trend correlation that higher mass galaxies have higher flatter density profiles, and we can use that in understanding and revising the rates of tidal disruption events in order to better constrain how often black holes will happen in them, tidal disruption events will happen in them, and then that allows us to take the information that we'll get from Rubin and turn it around to understand what the demographics of black holes are in galaxies. So here's an example of that in this plot. You can imagine that, if you have the two different scenarios I talked about before, this scenario where you have lots of low mass black hole seeds, then the tidal disruption event rates that we would see would have more low mass events. Whereas if you have this direct collapse scenario, you might expect more high mass events, and then there's kind of a threshold where you don't see black holes anymore. And here is some sort of simulation of even just 20 measurements would be able to maybe distinguish between these. And we're going to have many more than 20 measurements. But the problem is we really need to have those measurements in a way that doesn't have strong selection effects. I have a student, Christian Hanna, right now, who is working on improving the rate predictions using observations of nuclear star clusters. And then we hope to compare that to Rubin data to constrain black hole demographics. So that's all I have for you. And I'm happy to ask questions now, answer questions now.
Yeah, thank you, sir, for your wonderful presentations. So we have got few questions. If you allow, we can start our discussion session.
Yeah.
The first question is, sir, is there any evidence for wormhole, or it is just a hypothesis?
Yeah, so it's just a hypothesis, and not only that, it will always remain, I think, a hypothesis because we don't really have any observational way of probing whether black holes are, somehow connected between each other. Because we can't actually see anything after it falls into black hole. In fact, we never actually see stuff even ever fall into the black hole. What we see from our perspective is the stuff slows down as it reaches the event horizon of the black hole and actually gets, because of time dilation, we actually never see it fall into the black hole. So we can't even see the material falling into the black hole, yet not anything coming out of it. So basically, there's no way to verify that idea.
Sir, thank you. There is another question. So which books would you suggest me to learn about physics as a student of class 10?
I don't necessarily have good suggestions for you. I think that there's lots of great popular astronomy books. I just finished a biography of Cecilia Payne-Gaposchkin, who's the person who discovered that the universe was made primarily out of hydrogen and helium. I think that's a great, just reading, before you're taking physics courses, just reading about the kind of background is maybe the most enjoyable, fun thing to do. And then, your courses will give you, there's of course books, there's like the Feynman lectures, there's things like that you could read, but they're pretty widely available. But I think, my feeling is learning physics is best done through doing physics, solving problems. And that's the kind of thing that just reading a book won't help you with. I don't know.
Thank you, sir. Is sun orbiting a black hole?
In some sense, yes. So, there's a black hole at the center of our galaxy, and we're moving around our galaxy every 200 million years. But that we would be moving, even if the black hole wasn't there, we would still be orbiting in the same way. The black hole has no impact on our orbit. So, yes, we are going around a black hole every 200 million years, but that's just because it's at the center of our galaxy and we're moving around our galaxy. The collective mass of all the stars in our galaxy are creating the gravitational potential that we move through.
Okay, sir. Thank you. This may be the last question. So, are stellar black holes gravitationally bound to supermassive black holes?
Yeah, that's a great question. So definitely not typically, but the question is, can that happen? And the answer is definitely yes. One of the questions that we have at the center of our own Milky Way is, what is the population of stellar mass black holes around the center of our supermassive black hole? And that's actually a very hard question to answer. It's very hard to detect those black holes. And so the answer is almost certainly yes, there are stellar mass black holes that are gravitationally bound to the supermassive black hole in our own Milky Way. But we don't. It's very hard to probe what that kind of distribution of stellar mass black holes actually is.
Seth, so thank you for your wonderful presentation and discussion session. The main aim of our program is to motivate our students. I think by your exciting lecture, some of our students must have motivated. So thanks again for giving us this opportunity.
Thanks for inviting me. It's a pleasure.
Bye for today.
Okay.